I am gonna present. This is I'm one of the organizers here, right? So I can't present my own. So I want to talk about at all. Which is the Toric code, and it's very new and very it's also a bit for us because I mean I come from this upstart, young, kind of successful, but looked at it a bit critically from the older guard field of quantum information. I think it's maybe similar to like compressed sensing in applied math. And there are these old established players, and in our case, it's condensed metaphysics, this big, huge industry of people that gets all the job and all the monies. And I believe it's like PDEs in applied math, right? So we have a bit of an uneasy relationship. And what happened a few years ago is that these condensed matter people actually started listening to us. And this was what I'm going to present today was a big reason for why that happened, right? So it's some quantum information technique that really changed the way condensed matter physics and condensed matter theory worked. All right, so that's the Toric code. Of course, torus, and vertices on the lattice, and this cyclic boundary conditions. So if I'm on this vertex and I move down here, I wrap around, and here I also wrap around. So the basic objects are k by k lattice on the torus. Yeah, actually, we are going to be mostly the more important objects here are not the vertices, but the edges. How many edges do we have? We have 2k squared. Yeah, why that? K squared because it's square. Twice as many edges as we have vertices because it takes these 4 edges, but every edge only 2 vertices. Okay? So this counting will become important. And now what we do is we associate every edge a Hilbert space. So the most important object here is these are all the objects. Right? So we have C2 tensor C2 tensor C2, and these are n times. And the way I think about it, and the physicists think about it, is that every vector space, that the individual C2s live on these edges. Right? There's a C2 attached to every edge. And if you think that's a bit bizarre, you can also just label all the edges, I don't know, 1, 2, 3 in some way, and then every edge would refer to the ith edge would refer to the ith factor in this tensor product. Right? So now that I have this, I can start putting Weyl-Heisenberg operators on these edges. And this is meant to define an operator on this tensor product. And what I do is I take all the Weyl-Heisenberg operators on the edges, and I just tensor them together. So if on the first edge I put sigma x, then what I mean by this is the operator, which is sigma x on the first factor, and then plus the identity on all the other factors. Matrix acting space. And the only Weyl-Heisenberg individual operators we'll need are sigma x and sigma z. And of course, tensor products of these. Yeah. So that was a single one, but I can label more than one edge if the first edge is labeled sigma x and some of the ith x edges labeled sigma z. Then by this I mean the operator that is sigma x in first place and sigma z in the ith place, and identity elsewhere. All right? Yeah, does that make sense? Okay. So now I will introduce 2 kinds of operators, of Weyl-Heisenberg operators. And these will be the building blocks of everything. And the first is vertex. I associate the so-called star operator. Associate the star operator and the star operator is, and yeah, now I should color code this, right? Is x v for the vertex, and that is the product. Let me first draw it here. So here's a vertex, and now I look at all edges that are adjacent to that vertex, and I put a sigma x operator on all of these. Sigma x, sigma x, sigma x, sigma x. Right? And this defines an operator by this convention, a Weyl-Heisenberg operator, and that is the star operator associated to that vertex. Right? So it's a product over all the edges which are incident to V. Sigma x, and now this notation means the sigma x matrix, the ith place, and identity elsewhere. Right? So that's the star operator. But I'm not done. I have some kind of dual object, and the dual object are the plaquette operators. And a plaquette operator will be associated with every face or plaquette. Right? So if I have a face here, then here's the face. Then to all the edges adjacent to that face, I put a sigma z operator. Z, 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 z. Right? Okay. To every face, associate the plaquette operator. And let's call it capital Z, face, and that the product over all the edges which are in the boundary of that face, and it's going to be sigma zi. Okay. So the rule of the game is now that I will analyze the group generated by these two operators that live on this torus. Yeah? So first, so let's collect problems. All right, so now facts about these operators. All the star operators, they mutually commute. That's obvious because they only involve z's and identities, and all the plaquette operators also commute among themselves. That's also obvious. What's also true, and that is the consequence of this construction, is right? So we have that every star operator and every face operator commute. But the reason is very simple, because sigma x and sigma z, yeah? But if I take some plaquette and some star, then they either live on disjoint parts of the lattice, and then only meet at identities, right? So they never in the commute. Or if they do meet, if I take the star operator that has some overlap to a plaquette like this one here, then by construction, they will overlap in two places. And if I commute them past, I incur a sign of -1 here and a sign of -1 there, and they cancel. And so they also commute, right? Because they always meet an even number of places. Okay? And now this is the first time where this geometry enters. All right. Okay. So that means that these operators generate an abelian group, and this will be very important. So S will be the abelian group by all stars and all plaquettes. Yeah. It will analyze this group. And, it's easiest for when I multiply cat operators. So what happens when I'm okay, so let's say I want to look at, maybe I take some U space here. So I'm going to multiply the plaquette operators associated to these plaquettes. Right? So this plaquette gives me sigma z's on these boundaries. And what happens here? Right? This vertex is associated to the upper plaquette, but it's also associated to the lower plaquette. So on this C2, there will be the action of 2 sigma z's. Right? But because they square to identity, it will cancel and nothing will be here. Here I will get a sigma z. Here again, I have 2 sigma z's canceling each other, so there's nothing. And so that's what I get. So I get a closed chain of sigma z's, and they delineate exactly the boundary of these plaquettes that I multiply together. Okay. We can understand now, at least we can understand the subgroups generated by the plaquette operators. So if I, for F set of plaquettes of system, we have that the product over all associated plaquettes is the product over all boundary of F. And then we have the sigma z acting there. Okay, so now already, if you have had some exposure to this kind of math, if you hear torus and chains and boundaries, you can maybe see where this is going. Right? Now, that thing is going to enter next. Because, okay, so can you, all right, so the kind of operators I get by multiplying together faces, they give me closed chains. Is there a closed chains of sigma z? Is there a closed chain of sigma z thing that is not contained in the group S? Is there a closed chain of sigma z's? I can define it, commute with everything, not the boundary of some set of plaquettes. The key moment. Ha, Ingemar. Yeah, exactly. All right, so we need some closed chain. Look, if I have a closed chain, then it will, of these, it will commute with all the x's, because a closed chain will meet every vertex number of time. Right? This is like the old Königsberg bridges problem, right? Because you have to move, it's a closed chain, you have to move into the vertex and move out again. That's an even number. Yeah? So, so if you have a closed chain, it will commute with all the sigma x's. So now you need a closed chain. It's not the boundary of anything. So you need some chain, the boundary, and of course we know the chain that is not a boundary, that is described by, well, if you want the first homology class of the thing, geometrically it's described by going around the torus in a non-trivial way, right? That's a closed chain, and it's not the boundary of anything. There's a second one, which is not the same. It's equivalent. Namely, I can go like this around the torus, right? So there are 2 strings, and by this I mean, okay, take some line here and apply sigma z's there, and take some line here and apply sigma z's there. This will commute with everything, but it's not the construction. Right? This will be very important. Okay, so a closed chain of sigma z's along a non-trivial topological trivial loop commutes with S the group by the cat and face operators, but is not an element of S. Yeah, there's 2 such there's two such loops. And by two such loops, I mean up to boundaries, right? So if I have this loop, of course, I could also have taken this loop, but they differ by the boundary of this area, right? So with an element of my Z group, I can do the loop along the torus, and I can deform it. So we have all the ingredients of topology, but I can never unwrap it. Okay. And this also means already that we can do some technical counting. This will be important. And now Windows wants to know who I am. Shall we do this now? Yeah, probably. Okay, so now we can count how many the size of the group generated by the plaquettes. So I take all the plaquette operators, I take the closure of the group, and then I get. Okay, so I have k squared. I have k squared generators, right? One for every plaquette. And the relation is, yeah, they're all dependent because if I will get the boundary of this. Yeah. So boundary, I can cover the area, so I can cover together. So basically, there's no relation. It's not true here. It has no boundary, and that's the entire torus. Yeah? So speaking differently, if I apply all of these plaquettes together, I just get the identity. That means that every edge will be hit twice, right? They all cancel. So the only relation I have is that, I should state that first. So only relation in this group, the plaquettes, among these plaquette operators is that the product of all of them is the identity. Cardinality ZF k squared minus 1. Is that right? That is, yeah, that's right, and that's important. Okay? All right. So now the same analysis works for the star operators, and there you don't get. You can shift it to the letter somehow, right? You can basically do the same. I will not tell you how it works, but it's also exactly topologically not a way of getting star operators. You will have exactly analysis up to some duality operation, which I can explain to you if you ask me later. Right? So same for or analogous for stars. And now we can compute. So we also have one relation. We also have the same sign. We can compute the size of this group. Because certainly no relation between x's and z's, because I mean there's no way I can get an x operator. So in the end, the size of the group S will be 2 to the 2k squared minus 2. Yeah? Right, for the x and one for the z types. Any questions? Okay, so my plan was to sweep that under the cloud. If you extend me some credit and just trust me that I'm not, maybe I can tell you later. Yeah, it's exactly the same. Oh, this. Yeah, all right. Okay. So fine. And now, all discussion here, we have kind of felt that topology enters somehow, but what do we do with that now in physics? And now we go. So this was all just some operators and some tensor product space. So what do physicists do? And they write down a Hamiltonian. So now I call a Hamiltonian, but you don't actually need to know what that is. I form this matrix. H is minus the sum over all, and then the star operators, sum over all plaquettes. The plaquette, yeah? And this I call a Hamiltonian, just because that's how I was brought up. And a Hamiltonian, in whichever way, somehow describes the energy of a and how. One thing we want to do with this big matrix, it's a big matrix on a product space, and we want to understand the low-lying eigenvalues, so the small eigenvalues, and the small eigenspaces. And it's associated with understanding the low energy behavior of the system. Okay? So the goal is understand the low eigenspaces of that thing. Yeah? And just one comment. So all these operators I'm summing together here, they act on a few. Philip, you want to? Sorry. This is completely irrelevant. We know it, but all right, you don't need to do this now. This is important now. So, okay, so now you have the. All right, this is actually that important just to make it. So one reason why it's justified to call it a Hamiltonian is because all these terms here, they act really only on a few tensor factors, maybe only on 4, every summand here. And that has to do with the fact that interactions in nature are two particles close together may see each other, but far apart they don't. And so this is, at this level of abstraction, this is physicists would call a local interaction. Yeah? But even though every summand here is somehow local, the behavior of this matrix, the matrix will depend on the topology of the space. Get people giddy. All right, so the dimensional eigenspaces. And what do we mean by that? Well, I mean, for one, we can find out what the smallest eigenvalue is, which I will call the ground state energy. And we can work out the degeneracy of this lowest eigenspace, which I will call the ground state space. Then something happens, which will probably not interest you at all, but I will try to convey why it's interesting, and which made a big splash in condensed matter theory. All right. So what is lambda min of H? Well, okay, I mean, it's very easy, all right, because it's a very high dimensional matrix, but it's defined in terms of small matrices. So there is a hope that I can find eigenvector to all of these matrices that is so every summand here has spectrum plus. So I get a contribution of -1. I can, but if I compute this, I can find an eigenvector that has -1. And so there is a k 2k squared is -n, right? So it's certainly larger than that, and maybe I can meet this. Yeah. And now here's a lemma. So here's a lemma. So it's indeed equality. So the smallest eigenvalue, you can do this. You can minimize them individually. So lambda min of H is indeed equal to -n. And what is more, the ground state degeneracy, so the degeneracy of eigenspace is 4. And lastly, and now comes the thing. This eigenspace is against any local perturbation. Maybe state this vaguely here, and then we'll do a sketch theory argument. So this eigenspace is It's incredibly, right? It's incredibly stable. Stable, it will make physics great again. Against any local perturbation and adhering to this political tradition. I actually say here what I mean by this, but I will say later. Against any, so it's not quite Trumpian, local perturbation. And how just very simple Weyl-Heisenberg theory. So that's the beauty, because second I will tell you how this argument upends one of the basic tenets of condensed metaphysics. But in the end, all we need is basic Weyl-Heisenberg theory. Okay, so here's the proof sketch. Okay, so I mean, I can meet a joint of all these eigenvalue minus 1. And to find this, the following. I define an operator P, which is 1 over the size of this group that I find, the group generated by these terms, and then I sum over all elements in the group, and that's it. Yeah? So that's an operator. Yeah? If you know some representation, you can see what's happening here, right? Because that's a matrix, BD matrix group, and I sum over them. So what I will get out is the projection onto the trivial character, right? Onto the joint +1 eigenspace, right? And +1 will be the smallest because I have minus signs in the Hamiltonian. Yeah. And so, I mean, I can prove this if we don't know representation theory. So then, so P is Hermitian. Yeah, it's Hermitian because every summand is Hermitian. Yeah. P squared is square that I just have a double sum, and the group, I'm summing over the elements of a group. I will, in this double sum, I will just rearrange time, so I will just get the same counted many times. So there's a multiplication factor that I can use, so that P squared is P, and I've already a factor for U, right? So P squared is P. So it's an operator. Now, what is the dimension of the space it's projecting on? Well, look, that's a trace over Heisenberg groups. It's 0. Yes, I hit the identity. So if I hit the identity, so I hit the translation factor. If I hit the identity, I get 2 to the n, because that's a number of the right? It's the number of tensor factors. Yeah? This 2 to the n minus this over 2 to the n minus 2. Now that's why counting these relations was important, and that's 4. Yeah, and now final thing to do with that, P is PS is P and S. So arrangement, right? Summing over the entire group. If I multiply from the left, I'm still summing the entire group, blah blah. And so this means that I have a joint. This P projects on a space of joint +1 eigenvectors to every term in there. Yeah? So it's actually a ground. It meets this bound. Yeah? So we used nothing but extremely basic Weyl-Heisenberg to show that. Okay, now you say bummer. So there's the matrix and it's degenerate. But big reason why people are very about this, because you see, degeneracy is a non-generic behavior. If you manage to write down a degenerate matrix, there must be some mechanism that led to this degeneracy. So degeneracy is worthy of an explanation because it's generic. And you can say, aha, but it wasn't a random matrix. It was a matrix, was a sum over terms, and every term was defined locally defined on a small number of tensor factors. That leads to degeneracy? Answer, no. If you choose randomly, mechanism, some of these terms like that. Take no, usually that's not usual, right? So that you don't say that. Nobody would say that. Sorry, this is yeah. Please don't say that. Yeah, symmetry. Aha, symmetry, exactly. So how do degeneracies, quote unquote, usually arise? And so the answer that I mean, physicists don't prove stuff; they have their opinions, right? And the opinion that is absolutely totally accepted is somehow that the behavior of these Hamiltonians is governed by symmetry. And here's like the standard example. It's called the Ising model. Yeah, and it's the only thing that everybody understood in physics, and so they just generalized from it to the world. So the Ising model would be another Hamiltonian, this time not on a torus but on a linear chain. And so the Ising Hamiltonian. And it's of the form sigma z on the first factor, tensor z on the second, tensor identity, which I don't write out, plus second, tensor sigma z on the third, yeah, sigma z on n minus 1, tensor sigma z on n. Yeah. Okay, so what is the ground state? What is the lowest eigenvalue here and associated eigenvector? Well, look, I mean, sigma z tensor sigma z. If I take an element of the standard basis, yeah, so then this gives me a sign, a -1, if I have the second element, and the +1 if I have the first, and if maybe I want to have minuses here. So the Hamiltonian has minuses here. So if I want this eigenvalue to be +1, then the first two factors have to be the same. Let me just write out the answer. It's easier to say. So the ground state, so the a basis for the lowest lying eigenspace is given by E0, so E0, tensor E0. Because this term says the first two have to be the same, and that's done. And this term means the next two have to be the same, so they all have to be the same. Of course, being the same, I can also achieve by E. And so this Hamiltonian has a twofold the lowest lying eigenspace, and because the constraints say all these factors have to be the same, but agnostic as to whether they are 0 or 1. Right? So physicists would call this like up, 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 and this down. Yeah, so they would associate this vector with a magnet pointing in this direction, and this with a magnet pointing in the other direction. And the Hamiltonian would say, this term would say the first magnet's got to be the same, the second two magnets got to be the same, and so on. But clearly, now there is a symmetry between if I just flip every single spin, every single magnet, if I just interchange E0 and E1 simultaneously everywhere, obviously you get another ground state. Yeah? And so one thing about symmetry-induced degeneracies is that they're very fragile. If I now add another term, if I now add the tiniest perturbation, some external field that tells me I prefer magnets to point up rather than down, immediately the symmetry is broken, and one of the two elements is selected as the new ground state. Yeah? So I can act a tiny local perturbation on put the term, which means there's a tiny magnetic field spin, just one of them, and bang, the degeneracy is gone. Yeah? So if I look at the Ising Hamiltonian plus epsilon sigma z on any of the spins, immediately I'm going to pick up a plus epsilon energy penalty, and this one is going down by epsilon. See, broken. Yeah. By local perturbation. And for decades, people were thinking that the only mechanism that we have in physics is creating degeneracies and resolving them. Now comes well, I mean, were early examples. Toric code was the first understandable, and I can show in 5 minutes that this graph computed there is extremely stable. Yeah, you can add anything that's local, supported on a few any operator that supports just these edges, not to extreme perturbation theory, not affect the ground state at all. And this is important also physically because if you think about this thing as an actual terms on which actual particles live, that are actually action, yeah, then if I tweak the interaction a little bit, this doesn't affect the ground state at all, unlike here. Yeah, this is a big race. Yeah. Tenders for these things are is Charlie Marcus in Copenhagen. Scandinavians might do this race, but it's a bit. It's also, I mean, it's also not so clear when you declare victory. Like when have you succeeded with working? Yeah? Unlike the nomination process in the US. Right? Okay, so in contrast, so the P is stable. And in order to show you how that works, let's look at an excitation. So we don't ground state. Now let's look at the first, at the next highest eigenspace. And in fact, let's do this. Okay, so now somebody comes along. What happens if I take one, then add the x? Well, look, this affect any of the star operators that are away, any of the effect will. Do I want a sigma z? Yeah, maybe. In fact, it will not affect any of because it commutes with them. However, it is adjacent to where I applied my sigma z. Yeah, this star operator and this star operator, they will somehow happen here, which they don't commute. Set out what that is. Okay, so let psi in range P be a ground state. Be one of them. What happens to sigma on the ith side acting on psi? And this will turn out to be, again, an eigenvector of the Hamiltonian, but it will be a higher for a higher energy. Okay, now what is h of sigma di of psi? Well, in order to calculate it, let me put an identity here. So I'm only using the basic of Weyl-Heisenberg theory, so they squared 1. Yeah. And now this means I conjugate every term in this Hamiltonian with sigma. Right? So all the terms will commute except for these two letters, which will flip their sign. Yeah, but it will still be an eigenvector. So that is the final sigma z will survive on psi. Now I've changed two phases. So before I had an eigenvalue of n. If I change the sign from -1 to +1, I get a penalty of 2. And twice I get a penalty of 4. Right? So that is -n-4. Yeah? Again, an eigenvector. You can see that this is actually the smallest excitation you can create. You could think maybe I can just single sign because the solution is so if you switch one sign, that the product remains unaffected. Yeah? All right. And now we have the following cases. Right? Now, arguing as we did here, we have the following cases. So let D be any Weyl-Heisenberg operator. So any product, tensor product of sigma z, sigma x, sigma y is on the lattice. There are three cases. And then we're almost done. Case one is D is an element of the stabilizer group, in which case it does not change ground states at all. Right? So D is a definition trivial on ground states. let's say, psi is again a ground state on psi. B, D is not in the stabilizer group, and in fact, there exists some element with which it does not commute. There exists an S and S such that S D is not 0. Then, by the very same argument we had here, it will map any ground state to an excited state. Yeah, so it will get you out of the ground state space. Right? So then, d psi is orthogonal to the ground state space, the range P. Yeah? So the only way I can act non-trivially within the ground state space is if I have an operator that commutes with all S, but is not an element of S. Yeah? So the remaining case is S, S, ds is 0. It commutes with the entire stabilizer group, but D is not an element in S. So then this can act non-trivially within the ground state space, but we've worked out in the very beginning that the only way to do it is to wrap around the torus in a topologically non-trivial loop. Yeah, so then, well, I mean, we've kind of seen that, right? So then one finds, arguing as before here, that D contains a non-trivial loop. All right, so now we have everything. We can now prove that that thing is stable. So now take the Hamiltonian plus delta, where delta is each of which are right. These twos are affected. 2 is not really important. Where delta is sum over terms, each of which sum over terms, each a living on 2 edges. Yeah. So then I want to use a perturbation theory to see how this affects my ground state space, and so K, L, M. What do we not have? L, right? L's order perturbation theory depends on what? Delta, you take the Lth power and you sandwich it. You see how this acts within the, you compress it to the ground state space, right? So that's what perturbation theory tells you. Yeah. But this can be non-trivial only if it has a non-trivial loop. But to have a loop, you have to have support at least of at least size k, right? You have to get around here, so the dimension is k. Right? But initially, we were supported only on 2 terms. The squared can be supported at most on 4 terms, right? I guess that's a twisted convolution, if you like. Yeah, if you multiply again, if you take it raise it to the 3rd power, it can be on 6 C2s at most, right? So this is 0 unless L is bigger than k over 2. And now k, I mean, we're talking about condensed matter physics, so you can easily think of times 100. Right? So then to 50th order perturbation theory, nothing to do literally around. So yeah, so we've engineered some interaction, some Hamiltonian, and what happens there in the ground state is completely unaffected by anything you do locally. Yeah? And that's a big, it's conceptually very important. People actually try to build these. And so yeah, so this is the beginning of the long story of the Toric code. It has more features that one can easily explain also with Weyl-Heisenberg theory. So most once you wrap them around, nothing happens. There's fermions, you do the same, you incur some sign. Yeah? And Anyons are, by definition, any species of particles that behave interestingly under bracket being wrapped around each other. And so what we've looked here is, so this sigma z action is created in excitation. This excitation can actually be interpreted as a pair of particles that now lives on this torus. So initially, the ground state we call the vacuum. So we have a torus and it's in some vacuum state. Somebody comes along, applies the sigma z operation, bang, a particle-antiparticle pair is born, modeled by this excitation. You can apply more sigma z's, then you can make them walk around the torus. If they ever meet again, they annihilate, they vanish. Yeah? And so you can instead of using a sigma z operator, you could use a sigma x operator. It would create a different kind of excitation. And now you can check. It's like 5 minutes from here. So if you're interested, you can. How do they? If I now take a z excitation and a type excitation, and I wrap them around each other, or I wrap z type around x type, what happens? And it's easy to compute. If you wrap two z type excitations, x type is boring, but an x z versa, and you assign. So you have particles that behave like usual fermions somehow. Right? And so all kinds of interesting phenomenology you can derive, and everything I told you now, and everything I just sketched is proved using commutation and squaring to one of Weyl-Heisenberg operators, and that's really all. Okay, yeah, so that's the end. Yeah?
Why is it called the Toric code?
Ah, it's a very good question. So Toric is what's called a code. Okay, so space seems to be unaffected by local classical coding theory. There we have something that's vaguely similar, right? What is a linear code? A linear code is a subspace of a discrete vector space, such that any local action, which is also modeled by a vector in this, but any local action. Yeah. So that's what we have here. So the analogy is perfect. Code word and the errors are modeled by the same type of here by vectors in the Hilbert case, the errors are acting here. Yeah. And up to this, so it's less specific somehow between what stores the information, what models the classical coding case, but still the analogy holds up, and so this is actually the basis of quantum coding, yeah, which is important. Well, I don't know whether it's important, but should a quantum computer ever be built, right? It must work in a fashion that is resilient against errors. Yeah? And that's because how do you code in a classical context where you introduce redundancy, right? If I want to send you a bit x, but there might be some noise in the channel, I send x 5 times. Yeah, that doesn't work in quantum because of you can't replicate. You have to put it in a more genius way. And these spaces in a tensor product space that are unaffected by local operators. So these are turn out to be the right generalization of coding, and actually that was the initial motivation. Later the condensed matter people took over this field, but the initial motivation was quantum computation actually. That's called a code. No. There's why? So what do you want? There's before that that's 2 qubits, so you can store 2 qubits in there. Yeah. You can say, oh, that's lame, 2 qubits, wow, like 100 times 100, like 2, yeah. And you can work out though that if you don't start with a torus, but if you start with the surface of genus G, yeah. So then the degeneracy will be 4 to Yeah, so by punching holes into surfaces or creating these higher genus Riemannian manifolds, whatever, you can store an exponential number of dimensions or a linear number of qubits in there. So that works. Why? Okay. I'm not sure why you want to do that, right? Because classical information storage is, I mean, you can buy a terabyte for like 50 euros, so, and that's insanely stable. So I'm not sure all this coupling 200 systems to topologically protect a qubit is really worth it if you store a classical secret in there. So I think if it makes sense, I don't know whether it makes sense. If it makes sense, then it makes sense for quantum information. Or it makes sense for understanding new mechanisms for how global behavior arises in many-body quantum systems, right? And so you say that again. People yeah, so the effective behavior of the systems. I mean, what do we have in many-body physics? There's the surprising thing that you have some exponentially big Hilbert space and thousands of particles interacting, but often a few macroscopic parameters, I don't know, temperature, energy, symmetry class, allow you to kind of make good predictions about it, right? I mean, the standard example being water and ice, right? So the difference between water and ice is in ice you have a lattice, you have a crystal, right? And it has some discrete translational symmetry, absent in water. Yeah, so using the symmetry alone, you can already predict a lot of behavior of these gigantic systems. We have a new mechanism for globally accessible behavior, and that is not due to symmetry, but to topology. I think of this like the genus, yeah, and so we have interaction that only our nearest neighbor, right, that only see every C2, every particle on these edges only see 3 other ones. And still, their behavior depends on properties of the space they live on that, by definition, are in under local deformation that only can be globally defined, like the genus. Yeah? So that's why people are insanely excited about that, even if you will never use it to store quantum information or classical information. Well, I'm an expert at this. So, why don't you ask Charlie Marcus? I don't know. So and these things are. This is condensed. It's all solid state, superconducting, solid state based type of stuff. And then actually, I don't know. Don't tell is it still recorded? Don't tell my colleagues. So this is really too complicated to explain. Ask me, I will. Yeah. That should really not be so egoistic and think about the non-physics audience. All right. Any questions that the answer to which I would be comfortable to have recorded? Yeah, but the, yeah, you can do this. So you will always be. I think this is one of the fundamental differences of interest, right? I mean, if you if you listen to Werner Kotzek, he barely distinguished between finite fields and reals, right? He talked about small things and underspread and being close to the origin, right? So always implicit was you have like one group of very high order, yeah. And so always somehow in physics, like what makes the thing is that for every physical particle we have a tensor factor, yeah, and we have it in many particle physics. Of course, you can say instead of like 2-level particles like these spins or magnets pointing up and down, maybe we have I don't know, spin 1 which has 3 dimensions, right? Fine, that might happen. Maybe spin 2, 5 dimensions. Yeah. But I mean, there's kind of what it ceases to be interesting. But always you will look at this, you will fix a local dimension first and then tensor it to a very high power. So that's kind of the structure always naturally emerging. Yeah, and so can you generalize it? Dimensions? Yes, you can. Always you will be always the second limit will be, and now take many of these. It's kind of always where the interesting stuff happens. Yeah. Are you the chairman? Do you want to close the session? Okay. Yeah. Yeah. So I think actually we can come to the coding question. It's actually it mimics what you have there. Of course, you can also talk about codes about higher, about like linear codes about finite fields, bigger, and then it's immediately become more complicated because before you had Hamming weight as the unique measure of everything. Now suddenly you have weight, but maybe you want to distinguish not between 0 and 1, but 0 or non-zero. If it's non-zero, which exactly it was. So so it becomes more complicated. But of course it's doable, and it's potentially also the source of rich theory. Yeah. Yeah, but I think maybe the scaling up the dimension behaves closer to how coding theory would behave than maybe.
Why instead of like normal cyclic boundary conditions, you impose twisted boundary conditions?
Wow, the Toric on a Klein battle. Whoa, I don't know. What's the homology group of the Klein battle? Well, you're the mathematicians, right? So yeah, I mean, it depends. I mean, you can do it in general for surfaces with given genus, right? In the end, it depends on the first homology group of the surface, and cohomology also, because you got this duality operation, which I refuse to talk about, but because it actually takes a bit. Yeah. And if you like, open one and have what the homology group would be doing, like as our point geometry in the room. Okay, so yeah. Hey, did you say Richard? Yeah. You should not name the people. So long hair dude in the back. Okay, yeah. I mean, first, the cyclicity in the Weyl-Heisenberg is not at all even the same category. That's completely different kinds of things. My application is problematic because the interaction principle. What as of is I mean, I say, you take your solid state system and put it on a torus. You don't go to Charlie Marcus, he's an exponent in Copenhagen, don't tell him that, right? This will make him angry. Yeah? And so it doesn't really matter because you can engineer. So in the end, I told you this has all to do with the genus. So there's a variety of that, which is somehow slightly less elegant, but still works. And it's called the surface code, where you just take a surface without any boundary conditions and you punch holes into it. And you still get this behavior. So the people who are building it are not actually building the Toric code, they're building the surface code, which is somehow related, also sports onions. But here the theory is a bit nicer. And this is what people actually trying to build.
I think, is it important to ask it now? Okay,
Yeah.